Ladies and gentlemen, it's my pleasure and honor to announce the traditional Intel special on HPC, given traditionally by a man that was particularly relevant for my past professional life as a professor at TU Munich and as head of the Leibniz Supercomputing Center. Ladies and gentlemen, please welcome Raj Hazra, Corporate Vice President of the Data Center Group and General Manager for the Enterprise and Government Group at Intel Corporation. He has followed my professional life and he has also supported my professional life with his insight on computer architecture. So I'm very interested to hear Raj speaking about the convergence of HPC and AI and on the way to exascale. Please, Raj.
Thank you, Herr Bode. We need to stop meeting like this. Good evening. Good evening. There's still people trying to come in and sit down and take a seat. If you notice the title of my talk, this is probably the most accurate version of a number of things I could say. What I'm going to talk about is a particular paradigm change that's coming to us. It's been coming for a while, and we've seen snippets of it. In fact, if you were here for the last talk, you would have seen a very relevant example of that. But the paradigm change that's coming is accelerating. And it's really a paradigm change. It isn't about discussions of the last 10 years or so about, is it just CPUs or CPUs and GPUs? It isn't about whether you need memory and you need faster memory on package. It isn't about whether you program in parallel languages or sequential languages. It isn't about those kinds of important yet evolutionary changes that over a period of 10 or 15 years make it look like we went through a revolution, and we've gone through a few of those. I'm talking about a paradigm change that touches more than HPC. It touches more than the technology in HPC. It touches the way both the science, the technology, the infrastructure, government policy, and most importantly, us practitioners in this field have to change. It talks about, in my mind, a complete rejuvenation of what we've always called high-performance computing. And in particular, it's not a frightful change. It's an exciting change. This rejuvenation is at the heart and center for us as we look at the golden age of data. I'm reminded, when I said this, I get reminded of something that Justin Trudeau said. Sometimes the most obvious things are said most elegantly in the most simple sort of ways. For all of us who've done basic mathematics, we know this to be a restatement of the law of monotonous functions, right? Increasing functions. Yet, this has never been as true as it is today for the world we live in, we collectively live in, whether you're doing hardware, you're doing software, you're doing applications, whether you're defining policy and strategy at an agency level, at a national level, or even coordinating across that at a global scale. So with that in mind, if I say things here today that sound like I've seen that before, good, you're part of the paradigm change. If I say things or pose things that make you think that couldn't be true, and then you go off to think about why that's the case, I've succeeded. And most importantly, if what I say today makes you think about being excited to be in this new era, then I've really succeeded. Okay? So with that in mind, let's talk about what's making me passionate almost 30 years into my career here about the next 5 that I know will make those last 30 years of excitement and fun pale in comparison. What we're talking about is really what people do. It isn't quite first how they do it, what challenges they foresee, but what is it that people do? I've given you an example of 3 applications. There's many, many more. Many, many more. I'm going to look at this so that I can get this in order. The first one is around AI integrated in traditional HPC workflows. It's a weather climate application from NERSC. But really, it's about running climate simulations using GCMs, essentially using analytical modeling and tools. And then once you get to the output, using AI to glean patterns around particular phenomena in short-term weather or long-term climate that a human expert would otherwise then take over for. And doing it just as accurately, but perhaps more importantly, doing it much more quickly and efficiently. The second is a drug discovery application. I call it AI accelerating HPC simulations, because this is a complex process of understanding molecular interactions, of how drugs and their chemistry interact with those protein distributions, and then finally gleaning what the patient wants to know. The so what of all of that is, so what works for me, right? And this, again, is a combination of models where we understand how to model chemistry, but a large amount of this is where data has the answer, but there's no known analytical models. And with a combination of supervised and semi-supervised learning, we can actually glean more than what equations would ever tell us if you fed them inputs. The third is a high-energy physics simulation. This one is a very profound title from my perspective. It's AI replacing HPC simulations. This is a case where, in this particular example, cosmology simulations, lots of data is created on the simulations of particles and their pathways that's fed into a GAN network, and insight is gained at similar precision with what a simulation would have continued to run and do at a particle scale. So think about it. This is where AI, doing that through deep learning, this is where AI replaces simulation. And in many cases, we are starting to learn that our faith in analytic models is a little bit misplaced. There's loss of precision, accuracy, orders in which we can express them. And the data, if looked through how we would analyze data from an AI's perspective, actually has the answer. So in many ways, and I showed this for you last year, you look at a starry night, and simulation and modeling is your tool, you only see part of the stars. It's only through that lens of what you can model analytically in a closed form would you ever describe that space. The space is much larger, and sometimes the answer lies in that space, as in this case. So if you look at it from that perspective, we go, that's great. So we have two things, HPC and AI. What's so wrong about them? There's nothing really wrong about them. If you look at the trajectories, and as we watched over the last 5 to 7 years, or even maybe a decade of practice, they are developing. They're developing their own methods and infrastructure. They're developing their own ecosystems around that infrastructure. They're developing architectural models for storage, compute, network, fabric. They're developing software complete profit pools around companies that invest in tools as well as in infrastructure. And of course, they're continuing to drive forward, understanding what is being done with that infrastructure and making it better and better and better. But each to their own purpose. Each to their own purpose. That's the most important point. Two completely separate and disparate ecosystems. Two completely bifurcated, I would say till about recently, infrastructures with how systems are built. And I would say systems infrastructure for data-intensive versus compute-intensive scale-out models. And then, of course, at the nub of it is the compute requirements, going from double precision, floating point, to mixed precision, and then even the structure of that data, whether it's dense, whether it's matrix dense, it's vector dense, whether it's sparse, whether it's spatial, with regular and irregular control flows. So if you look at it, these two are on a path. These two are on a path to diverge, because each wants to continue the innovations that make it better this year than it was last year. The question is that okay? That's the question we face. So what's wrong with that? Is it okay for these worlds to live separately and go about their business as fast as possible as innovation will allow, and absorption of that innovation will allow. So the question is, and I'm sure each of you have an answer to this, is this the path we want to be on? If you look at it, my answer to it is that divergence is a path to oblivion for at least one of those paths. And depending on which of those you practice today and your biases and your needs for future preservation, you could pick. I see you smiling already, so I'm sure you've picked. Getting serious now, really what I've tried to draw is lessons from history. There was a time when we had visualization and compute as two completely separate tasks. We knew they were different parts of a workflow, but we had them as two completely separate infrastructures. They were divergent. You built your compute, you computed all of the things that you wanted to visualize, whether for human or typically for human endeavors, and then you had a completely different infrastructure called visualization. In fact, you built visualization caves, which is what I show on the right-hand side, for large scale, taking what was computational data output and turning it into visualization data input. Lots and completely different compute architectures, completely different storage mechanisms, completely disparate, so you needed a lot of data movement to come from one to the other in order to enable your visualization. And that just didn't last. Technology allowed us today to weave in visualization along with the computing of the data that was being visualized. It was both technically made possible with tremendous advances like ray tracing and global illumination, which essentially make visualization look like a very highly parallel compute task, and was made with innovations in the infrastructure that allowed us to put together systems that would not just be very good at both, but be optimal across the two. So, in a nutshell, from our perspective, it's cost, it's ecosystem dissonance, but perhaps more importantly, is the opportunity cost of not putting them together on a path to convergence. The things that can be only uniquely enabled from a workload perspective, as I heard the tail end of the last discussion from the National Cancer Center, right, is things that you could only do if you could do them quickly interwoven in a tightly coupled manner, where indeed simulation modeling and learning techniques become phases of a workflow, not two different workloads that have to coexist on the same infrastructure. So if that's the case, we have some work to do ahead of us. And that's what we believe is the mantra that we as an industry are focused on accelerating, working together. So if we have to create this, where it's one infrastructure, one ecosystem, and provide this solution, what is the first thing we need to look at? We need to look at what's driving the dissonance, or what's driving the divergence, right? And it starts at the heart of what we always see, is a system architecture. It's what we do our compute storage with, and how do we change that to be not one accommodating the other, but built best for both. So let's go on to that journey for a second. Converging the system paradigm really has three key attributes for us. One, it is workflow optimized. It's not workload optimized. It's not a capacity, like an old capacity HPC system. I shouldn't say old. Even today we have capacity HPC systems. It's not you and I will coexist without hurting each other. And our mileage will vary depending on the underlying system architecture. This is about, I will hand off to you my data, you will crunch, I will come back in, and we will work together, and the system will look optimal. Will look optimal for my work when I'm on it. When I'm executing, I'm the part of the workflow, and will look optimal to you. You are not paying a penalty for me being on the system. I am not paying a penalty for you being on the system. Right? That is the heart of workflow optimize. And I will walk you through why we believe that is hierarchical. It's a hierarchical architecture. It's a pooled architecture of resources. It's dynamically reconfigurable to deal with the various phases of a workflow. And it has the compute diversity needed to support the different kinds of workloads that make up a workflow. The second is around expanded memory storage hierarchies. In a data-intensive world, this becomes a fundamental either bottleneck or an opportunity for us to move forward. It's about performance. It's not just about performance at a hot to cold or cold to hot. It's about performance delivered through the various stages of temperatures of data. And today, that's increasingly becoming, with lack of locality, more stochastic. So you can't say this is drifting towards warm, this is drifting towards cold. You don't know what data you need when. And you have to construct hierarchies that can traverse those boundaries. The third is around software abstraction. And we sometimes in the hardware business or the systems business, the hardware infrastructure piece, completely ignore this. And we go, as we add more capability, as we add more choices, as we add more options, what does the person that's developing software for this do with all of these choices? You know, we sometimes spell choice as capability. I've given you choice. You can do whatever you want to do. Users see the same C word as complexity. And the industry stalls with the third C word, which is called chaos. Right? So unless managed through the system so this is usable, the same C word will show up over and over again. And it'll be either complexity, it'll be choice, or it'll be chaos. Right? That's what we have to manage through a software abstraction that makes it architecture agnostic. The work has to be architecture agnostic. You're not going to rewrite your code or even farm out your application with a particular hardware architecture in mind, and we'll talk about that. It has to be readable, maintainable, and most importantly, portable, and portable with some assurance of performance portability. You will not get the same performance on everything, but you must be able to understand the limits of what performance portability are as you select the architectures you're going to deploy on. So how would we build this system? How many of you today here in this room, you can just raise your hands, believe that such a system architecture already exists? It doesn't look a whole lot like one of the leading top 10 supercomputers in the world, I can guarantee you that. But how many of you believe that this exists? Or is in its nascent stages but exists? It does. It does exist. And it exists in some of the big hyperscale cloud service providers. Or it's starting to. Because this has to move away from the way we design HPC systems to be supreme today for a few workloads that fit that one paradigm, that accommodate AI without compromising that one paradigm. I'm going to point out a few things today on this picture. This itself could take an hour of very interesting architectural choices, and I guarantee you this is going to be debates for years to come. But I will at least lay down what I believe the key tenets of that debate are. The key word is composability. If you have to be optimal in different phases of a workload, you have to be composable to be optimal. If you have to support composability, you have to support modularity. Because without modular, you're always destined to provision for whatever your static configuration is. You have to go from fixed ratios of compute, storage, and networking to a much more hyper-converged, software-defined, composable, and physically disaggregated architecture. I remember the first time someone told me this, it was about 5 years ago. And I said, that's impossible. We won't even do virtualization in HPC because there's too much of an overhead, right? The paradigm was, when I answered that, and I've answered plenty of things wrong, but I learned fast, is it was the age-old method of you're computing on a core, and virtualization is simply an OS overhead that you have to go through in order to execute the same damn thing out of a virtual machine that you could do on metal, right? So why would I take that hit? But the paradigm is different. Today, I may move from one portion of the machine to the other. I may actually look for compute resources that aren't physically connected to me. And so they have to be software composable. So there are benefits I get that I didn't consider when I said my world is just fine. Give me node-connected, node-attached memory and storage and a network port, and I'm fine. Right? What this says, if you look at the rack, is you've got compute blades, and that compute blade may have, as I've blown up on the right, in addition, of course, to memory and storage access, right? You've got various flavors of compute, all connected into a domain. The key thing is, not only do the compute portions of this node understand who's next to them, they can also understand who's connected in a completely different rack and be able to reach out and connect to them semantically, right? So this is the basis of a composable architecture, from a node that has compute and storage, through the network, through a smart network port that is no longer a dumb forwarder of packets. It isn't just, here's the packet and that's the other node network I have to send it to. It actually understands compute. It's part of the compute hierarchy. And it understands where to place data, for instance, or takes part in the orchestration of that compute. One of the things you'll notice here is this disaggregation allows compute to move to data versus data having to move back to where you think you're going to compute. And that is a fundamental paradigm change. Depending on where your data is, was either created through the last phase of processing or comes in closest to a node, you're going to have to move your compute there. And that means the infrastructure must be able to be semantically connected to things, not just connected to it, but far from it. Think about what it does to paradigms like MPI, or even OpenMP on the node. And does the way we think about heterogeneity and locality even work with this kind of an architecture? As soon as I say that, someone's going to say, yeah, but you've never been a software guy, and that person would be true, would be correct. The complexity that comes from having to create such an architecture and manage it effectively is considerable, but the opportunities for value are just that much higher. You need to have an intelligent orchestration environment sitting across the racks, across what we would call the cluster manager, as well as the individual blade managers. Again, these concepts exist. You have a blade manager today. You have a rack manager. You have a cluster manager. In fact, there are companies that build software agnostic of vendors and other things for this. But they have to become intelligent. They have to understand where the workflow is and be able to place it. Sometimes using AI, ML, sometimes using the data that was created in the execution flow. Provisioning has to be application aware. Pull the right memory and compute for the job. By the way, as soon as I say this, our paradigm has been in the node. Get 2 CPUs and 4 connected GPUs. It may be that what you run on is the connected, quote-unquote connected GPU sits on not just another node, but on another rack, because that's where its data was created. Today, we can split up a discrete accelerator connected over PCI Express or whatever into multiple virtuals. This says I'm going to share that with a completely different rack, because that's where the data was created for it, or that's where I'm going to go in a sparse, non-localized, or non-uniform data access scheme. Right? You're going to have management that has to then provide a unified API to manage every module. and a control center in this complex infrastructure to understand what is where, because you haven't placed it. Today we know where we've placed it. In a hyperconverged infrastructure on steroids, you actually don't know where it is. So you need to know. You need to have telemetry in the system to know where what is. And that's new. That's a paradigm change. It's a paradigm change from, I'm going to place you, please work there, then tell me what you did, to this is what I need the system to do, and it will tell me what I need to know if I need to change the control flow. Right? That is an intelligence in the level of in the infrastructure that we have to create along with that hardware paradigm change of disaggregated and pooled. Again, I will tell you, if you are a large-scale installation where you're managing tremendous number of resources, and you have tremendously varying workloads, and you have tremendously complex workflows made up of those workloads, and you cannot afford what I would call TCO unoptimized or large overheads in your TCO, you will do this. You are already on the path to doing this. And when I describe those features, they are the challenge of hyperscalers. And so that's where we are seeing a tremendous amount of thinking going into how this system, this architecture gets built. So what are we doing? We're, of course, looking at not just evolving this in the future, but what our options are today for starting to put this architecture together. For starting that platform, then that becomes the basis, the very basis of experimentation, so that when we are back here 2 years from now, we can talk about not only the things we were able to do, but what we learned as well needed to change. In one of those views of what we are going to need in compute, we're going to need a workhorse, and that to continue to flourish and move forward. And that for us is Intel Xeon. One of our paradigm changes is what we've done is made Xeon the CPU for both HPC, with all the double precision flops, the memory, and other things you become used to, but added specific AI-targeted capability. We call it deep learning boost, right? So if you look at it, what we are not saying is the CPU will do everything. But what we are focused on is making the CPU capable of doing the things people would want to do on it for various reasons. Cascade Lake, so we have a strong roadmap starting in 2019 with Cascade Lake. VNNI, it's vector, the V stands for vector, the I stands for instructions, but really the easier way to remember this is it's called Intel DL Boost, which like AVX is an architectural concept which will have multiple implementations over the years in 19, 20, and 21, the three major generations of the Xeon processor. And what we will have is unique platform capabilities like Optane data center persistent memory connected to Xeon in order to allow new uses and new capabilities to operate on large masses of data that I'll talk about in a second. We are on track for Cooper Lake to be delivered in 2020, Cooper Lake, and then Ice Lake, which will be shipping again first half of 2020. Cooper Lake has now what's sometimes called the convergence format, or bfloat 16, for deep learning training. After many years of experimentation, there seems to be strong consensus that that's a great data format to go make happen, and we worked pretty hard to make it happen, not in a particular, kind of niche GPU or accelerator, but in the main workhorse of compute, which is Xeon. And we will have it enabled. So our goal is to continue to make Xeon the workhorse for the convergence era, and to be the most flexible and performant CPU that sits in that disaggregated, pooled, heterogeneous system architecture. What's available today, my little plug, is it's hard to not be able to say we can do something really useful when you have the highest DDR4 native bandwidth of any data center CPU today. The highest flops in a two-socket platform and the highest density with the two-socket platform on Xeon. You know, when you get to all these numbers, I mean, we've had a pretty good innovation run. I mean, things like 5.8x lead over competition is always a little bit satisfying. But really, it's that middle column that I want to call out. A 30x AI performance boost with Intel DL Boost. And this was our paradigm change in architecture. For a machine that always focused on what's your single precision and what's your double precision performance, what's the memory bandwidth required for it, what's the pipeline look like to make that the utilization on those two data formats the highest, to go in and innovate in one generation and get 30x improvement in sub-precision formats is stunning with very high efficiency. So we will continue to do this. At the same time, we understand and are pioneering new architectural approaches to providing workload-specific, and in particular, data-level parallel workloads. There needs to be highly parallel, there needs for dense and sparse, as well as spatial formats of control and data structures. We call it the XE architecture. We've just started talking about it, but we are busy working on it. It's the first 7 nanometer, the first product that instantiates the XE architecture is going to be on 7 nanometers. It will be powering the first US exascale system we've announced, which is Aurora, that will be delivered in 2021. And this is one of those things that we believe is transformational, not only because it brings the ability to have a acceleration framework or an architecture work along with Xeon just for the data center, but it goes all the way and scales from the data center to the edge. So that's kind of the next big thing that's happening and happening frenetically inside of Intel. The next part that we're working on is I/O. So I've talked a lot about compute, and you're saying, okay, here comes a chip company. Talked a lot about making compute more efficient, dense, and higher flops. What happens to memory and I/O? I'm showing you a few examples here, but fundamentally this is all about the transformative nature of Intel Optane Data Center persistent memory. How you can use this capability to actually transform the way you look at memory and storage as two separate paradigms. And this allows you for the first time to bring up what we call a converged memory storage paradigm. What does that mean? It means the simplicity of storage that you express when you send something to storage is maintained, but you get the performance benefit of treating it like memory. That's pretty profound, actually. When those lines blur, you get new levels in the memory storage hierarchy. And in particular, what Optane Data Center Persistent Memory allows you to do is to actually use storage in a memory paradigm. Some of the examples of this is higher bandwidth in applications like the one at ECMWF. We have a mode for this where the programmer has a fair amount of control in how data is placed in Optane Data Center Persistent Memory. Simulations that create lots and lots of writes. If you have to write them to conventional storage and go through all of that POSIX serialization, it makes it very slow. If you have to do post-processing on that data, the workflow slows down pretty much proportional to the ability to post-process, retrieve, and store that data back. With Optane Data Center Memory, all of that accelerates. In fact, you get 10 times the write bandwidth versus conventional storage. OpenFOAM simulations, 1,000 solver time step, 8,000 files with 1.2 terabytes of simulation data. The simulation runs 2 times faster with Optane Data Center Persistent Memory. Again, that bandwidth advantage. The third one is a very simple way of saying, instead of adding more expensive DDR that bloats the number of nodes just for you to host the DDR. More dense and more economical storage class memory lets you run more jobs and get more job throughput. Again, and if there's a way you can use the persistence portion of it to actually checkpoint restart or create other kinds of computational efficiencies, that's just gravy. That's not even in this. So again, we think of it as pretty transformative. But what's really, really exciting is the change it brings when we look into what it does for how we look at high performance data I/O in the world of data. Whether you're doing AI, whether you're doing big data analytics, or you're just running massive simulations. If you're dealing with lots of data, something in the infrastructure's paradigm has to change. And that change is uniquely enabled by something like Intel Optane Data Center Persistent Memory. I'm not going to walk you through a full tutorial, but this is extremely familiar to you. Today on the left, you have the HPC storage model. You have an application data set, and those data sets, for the lack of anything better, we say are blocks. Right? They have some locality to them, they have some association with each other, but there's multiple applications and their data sets. It today goes through a POSIX serialization into essentially a write mechanism, a storage paradigm of blocks, and the blocks get, by the storage system, associated and put down and written on whatever physical device. AI doesn't worry about blocks. AI worries and thinks about that data in key value pairs. Because there is metadata associated with every piece of value that is created, that's embedded in the key. It does not have this view of linearly looking for data. It has this view of, I will go find the data I need, where my key matches or key tells me. It isn't clear that if you went to this piece of data created at time t and stored at time t, that the next piece of data you're most likely to use was created at time t plus 1 and stored right thereafter. Right? That locality, that causality, is trumped by the association of the semantics of that data. So when you run it, and in convergence today, you run it through a POSIX serialization, you destroy that key value pair association, which creates the need to recompute that every time you want to use the data. And of course, you send it through a very inefficient way of in the same format, storing both your keys and values, right? So essentially what you've done is you've lost the data association that is key for processing that data faster. You've limited concurrency because you have to go look at serially through all of this data to go look at whatever you want. And of course, you've got low IOPS as a result of it. Again, it's a choke on the neck of this converged computing paradigm of HPC and AI workflows with massive amounts of data. The thing that to note is, what we are noticing is your flops to bytes per second ratio is 100,000 to 1. We worried as an industry quite a bit over bytes per flop when we talk about memory. I know when we were doing serious vector processing, we marveled at things that came to 1 byte per flop, right? Those days were almost like, when I was a kid and in Christmas I got 5 presents. Instead of in 5 Christmases today I get 1 present, right? That's how the world changed. But, at the end of the day, it was huge. And it still is huge to have that much imbalance, where you're spending money on compute and you're starving it. That's simply what you're getting in terms of 100,000 to 1 as your flops to compute ratio. We wouldn't even deal with 0.25 bytes per flop when it came to memory. And now we can no longer rely on just memory serving everything because of the size of data sets we have to deal with. So what do? Right? We create this layer called Deus. I'll talk about Deus in a second. What it does is truly, for storage and memory, the convergence between an HPC file-oriented, block-represented data set and a data set that doesn't understand any of that and simply has semantic associations of data. What Deus does is allows you to create this association and maintain it when you need it, and tunnel through the non-associated memory without any penalties, right? So if you look at what's on the figure, right, if you are on the right-hand side, you're no longer having to go through all of that serialization process, right? Most importantly, and this I want you to understand very, very clearly, it's only made possible because you have something like Optane data center memory, that little gray box sitting there. Because that becomes the performant cache for storing your keys, on which you would operate most of the time. Without actually having to pull the data out to see whether you're interested in that piece of data or not, right? If you didn't have Optane and data center persistent memory, and you simply said, well, I'm going to write to an NVMe storage, you would need gobs of DRAM, number one. Number two is you'd still have to write that metadata into storage. And there you would go through POSIX serialization one more time, because a storage device, your NVMe, is not going to understand, some other format. It still is block oriented. So this is a fundamental dechoker, and as I put below, what we've noticed and measured is it's still imbalanced, but it's a 10-to-1 imbalance. It's a 10,000x improvement in essentially efficiency of compute to being able to support and supply that compute with data. We can spend years working on more dense compute and getting our flops up and efficiencies of that compute up. We'll simply be starving that machine and that compute and that system if we don't have capabilities like this. I'm very proud to announce today that after years of working on Deus, that we are announcing that Deus is available. I've got 3 essential announcements. Deus is available on GitHub. We've actually written a solution brief that you can download from the Intel HPC website, and the solution brief talks about reference architectures and ways to implement so that you can go ahead and try out what you downloaded. And then we also talked, because we believe this is so fundamental to continuing to move the system architecture forward, the roadmap of features to come, and inviting the community to actually participate and accelerate the pace of innovation on this new storage paradigm. Okay, so this is very significant today for our teams that have been working at it, and our partners who've supported us and want to see Deus come to life soon in a system near you. The second part that is important then is what I had said earlier. Think, as you create the system architecture with all these phenomenal innovations in compute, storage, memory, and system software, what happens to the poor programmer? What happens to the developer? That is a huge effort on our part to see a world where it isn't fragmented by the origins of certain compute architectures and their native programming models. This is like going back to the world of assembly language programming, except now you may have 10, 15, 20, 25 assemblies languages to learn and write. We at Intel call it Intel's One API, or One API for hardware to the rest of the world. In particular, it's a unified programming model that to simplify development across diverse architectures. It's your choice. You want to run with an FPGA, a discrete accelerator, a CPU, a GPU style, an XC kind of like architecture. It's based on industry standards and open specifications, a big learning for us. Since the days when GPUs came out and other forms of acceleration came out beyond the CPU, was how important it was to keep it in open standards, so that for 2 things. One is it could be adapted more quickly, but more, the industry could participate in innovating and accelerating the capability that was available. And it's also interoperable with where the world has been and continues to be today, interoperable with OpenMP, Fortran, MPI, and other commonly used HPC programming models. The heart of this Intel One API, as you see in that yellow blown up, is essentially what we call data parallel C++ language and One API libraries for expressing this parallelism. It incorporates SYCL for data parallelism and heterogeneous programming, and it has language extensions driven through an open community project. Again, we want to see a world where programmers aren't worried about developing and learning specific architectures. They are focused and excited about getting their applications up and running and the value from those delivered with the most efficient and manageable set of resources they have. I'll do one more foil on why we are so excited about big projects like Aurora. It allows us to bring together these innovations instead of thinking about them somewhat discreetly and trying to put them together. It gives us the ability to put them together, to work with partners and the ecosystem to test, validate, and improve them. On the left is the Aurora system, the first US exascale system to be delivered. We're going to deliver in 2021. It's based on the Xeon Scalable processor, a future one at that time frame, with multiple XC architecture-based GPU in each node. It has more than 10 petabytes of memory. And it has 230 petabytes of storage, Deos-based, with a bandwidth of 25 terabytes per second, and it supports a full instantiation of Intel One API. Again, we've not made these public before, so I'm telling us ourselves for the first time today about the memory capacities, right? And we will have more to discuss as time goes on and we build out the system. But that encapsulates this big set of racks and doesn't actually talk about the smaller pieces of innovation that are fundamental in making something at this scale actually work. I want to highlight 4 things today. I will do that very quickly to say, without these kinds of innovations, you cannot build such a system, but most importantly, keep it up and running and usable. The first one is multi-OS. Multi-OS is basically Linux on a node plus lightweight kernels for better isolation, tighter control on resources, lower overhead. We plan to deploy this again, as I said, in the A21 system, working with Argonne, but we're also collaborating with other folks on building this paradigm, this lightweight kernel paradigm for how an application sees a stable Linux interface, but benefits from the performance boost gained by having lightweight kernels that can talk to that Linux kernel as well. A unified control system. Which is one scalable, coherent, easy-to-use capability. It should scale to more than 100,000 nodes. Again, part of this system and working with multiple folks to make this happen at multiple scales and multiple infrastructures. GOPM. It's a global extensible open power manager with so much with these systems at scale. Not just managing power, but just understanding from very accurate telemetry where power is being spent and why is very, very important. So it's on-the-fly monitoring and power rebalancing and better power manageability, including setting up some standards for how power data is created, communicated, and measured. The last one is PMIX, and this one, frankly, when I learned about it and the team was working with it, it blew my mind. Most of you, if you're writing MPI jobs today, know at scale, it could take hours just to get applications start because MPI is a very all-to-all connected synchronization mechanism. What the team did here is to say that is simply unacceptable. That kind of lethargy in the system just to get your job up and running is not going to work, especially as we build larger and larger machines and the workflows have very fine-grained duty cycles. So what do? we looked at, first with an MPI focus of creating kind of a messenger that says, I don't have to go do everything that every MPI rank does today, but I will create something that the resource manager can use, get a global view of the data, and get synchronization to happen faster without everybody having to talk to everybody, right? That cut it down from hours to minutes. In fact, for large-scale systems like top 10 systems, it's a 100x reduction in just application start time. But more importantly, we found, hey, this becomes a wonderful element, a very interesting and capable element of that hierarchical system management and infrastructure capability. And you don't have to just look at it for MPI. You can look at it for application runtime data. You can use it for resiliency data, or even power management data. And it becomes a new level in the system software that allows the kinds of gains we saw for MPI job starts to happen in other mechanisms, and not just at start and finish, but throughout the execution of a workflow. And we are very excited that other folks have joined us on this journey. It's a very large set of collaborations across industry and academia, and this is going to move forward. In 5 years, I don't know what it'll look like, but I am very, very sure that this will become transformative in the way orchestration and provisioning get done in these very complex converged systems. So I will then leave you with one question. I look forward to Zetascale, and I'm forcing ourselves and us as an industry to not have it in 2030. And I asked the question, if we were to write the top 500 list, if it still exists then, as a relevant measure of our industry's progress, what would be on that? What would be that system? That question mark is a meta question mark. It could be, what is the system used for? Is it an AI machine? Do people still run simulations on it? Is it in China, or US, or Japan, or Europe? Is it in a traditional large HPC center that put together its Zetascale program and got funded to do that? Or it's at Google, Amazon, Microsoft, Alibaba, Baidu, or some other CSP that says, that's what I'm going to go build? Who uses it? Is it folks funded to do massive science and research? Or people that are turning out applications on Friday, making $1 million over the weekend and putting the application away on Monday? These are massive questions for us to consider. This community that we've grown up for 40, 50 years is on the verge of a complete paradigm change. And the least of it, as much as time I spend on it, is actually the infrastructure and the technology. It's how we interact with each other, how we understand the very diverse natures of our businesses. It's how we collaborate. And most importantly, is how we stop saying, I'm going to accommodate you, to how we work together to create the new, what's in it for us. And with that, I'm going to leave you to think about those questions in the work you do. Have a wonderful ISC, and thank you once again for bearing with me for 55 minutes. Thank you again.